Well, this is the 8th of 12 presentations on the structure and properties of organic molecules. This presentation will be a short one. It just focuses on the naming of alkanes, or haloalkanes or cycloalkanes. Most important to this presentation is the understanding that you'll have to find a parent and groups within any molecule in order to name it according to IUPAC rules. So I've circled here what is the parent, as we'll learn later, is the longest chain of carbons, unbroken carbons. That if we circle that, that will also define our groups. So in green should be this whole length of 5 carbons, 1, 2, 3, 4, 5. We'll learn that later on. It's called a pentane parent, and we have off of that an ethyl YL group. So finding parent and groups is a very important thing to do when you're trying to name a molecule. And again, this should be all covered in green. Now you may be asking, well, couldn't I have gone 1, 2, 3, 4, 5? Yes, you could have, and you would have the same parent, not a different parent. Same name, so it would be the same molecule. Let's look at first, just kind of a review, really going back to the first task, drawing structures for a molecular formula and having that as a skill. We said we can look at molecular formulas all the way up here to C5H12 and try to draw constitutional isomers that fit that molecular formula. Well, methane, we can't draw a skeletal representation of it. It's just there's only one way to make a molecule that matches this molecular formula. And same thing for ethane and propane and butane. And you say, well, where did you get those names? Well, most textbooks will have the name for hydrocarbons, wherein you have 1, 2, 3, 4 carbons in a chain. They'll have the names provided, and it'd be good to know methane through decane. That is 1 carbon through a chain of 10 carbons in a line. These are names that are very commonly known in organic chemistry and used. But we can go beyond just for butane and pentane. We can go beyond a straight chain of carbons in a zigzag conformation. For butane, we can pick up the methyl group and place it on the middle carbon, having a longest chain of 3, 1, 2, 3, and something off the middle. Now there's a special name given to this constitutional isomer of butane. It's called isobutane. Iso is a name associated with any molecule wherein you have 2 methyl groups off of a CH carbon, 2 methyl groups within a hydrocarbon, and you can use it in other structures, but within hydrocarbons we can say if we have 2 methyl groups, CH3, CH3, off of a CH group, that's called an iso group or an iso pattern, and then we have to just count the other carbon and we get 4, so we can say 1, 2, 3, 4, but is associated with 4 carbons, so isobutane. We can do the same thing with isopentane. The iso pattern, 2 CH3 groups off of a CH carbon, again a carbon having 1 hydrogen here, and then counting the other 2, that would be pent, associated with 5 carbons. 5. And then last, neopentane. We'll say, well, isn't this an iso pattern? Nope, there's no CH group here. So they give this a different name. They call it neopentane. Neopentane. These are the ones in blue that I'll ask that you know the common names for, and these are accepted by the IUPAC Association. Now, all of these hydrocarbons are considered as saturated alkanes, meaning they don't have rings or pi bonds within them. Don't forget that these constitutional isomers for butane or for C4H10, butane isobutane, have the same molecular formula but differing connectivity. Now, how do we name just parts of a molecule? Like, let's say we want to point to some part of a molecule and say, hey, at this carbon, this one right here, we see this particular effect or whatever. You can do that with alkanes by naming portions of the full molecule, not the whole. So we can say for unbranched, I just wanted to use this term, unbranched or straight-chained alkanes, where we don't have to lift our pencil or pen. We can say for this unbranched or straight-chained alkane, we have 2 methyl carbons. Methyl carbons are carbons that have 3 hydrogens off of it. Methylene. Methylene carbons are those that are CH2 group with 2 carbons off of it. sp3, still sp3, but differing in number of hydrogens. This has 2, this has 3. So methyl, methylene. Again, we're just naming a part of the molecule. Branched alkanes, we're going to have a different name associated with the carbon here at this branching point. This is called a methene carbon. Now methene carbons have another hydrogen there that's not shown, but it has 3 carbons off of it. So we have 3 methyls, 2 methylene carbons, and 1 methene carbon. Here we would have 2 methene carbons and 4 methyl carbons. So getting to know the names of parts of a hydrocarbon are important. Methyl, methylene, and methene. We can also refer to these sites as primary, secondary, and tertiary, and there's even quaternary for carbons that have 4 carbons off of it and no hydrogens. We'd say a quaternary carbon. The hydrogens on those same carbons are called primary hydrogens. So secondary carbon, secondary hydrogens, tertiary carbon, tertiary hydrogens, and of course quaternary carbons have no hydrogens. So these are just the 2 ways, by numbering or by naming, we can refer to parts of the structure. Don't forget, or something I just want to point out properties-wise, lower boiling points are often seen for structures that have increased branching, such as for this constitutional isomers of hexane. Hexane is the name of this molecule. This would be a isomer, and so also with this, of hexane. These isomers would have lower boiling points. This one, a straight chained alkane having fewer branches, would have a higher boiling point. Lower boiling points are seen for constitutional isomers that have increased branching. So lower boiling points for those that have more branching. All right. Now let's get into the naming of the full molecule, not just parts. We have to define parent and group. Groups or substituents are parts of the overall structure that are considered as off the parent chain. So it becomes imperative to find the parent chain, because that's how you identify the group or substituent. To identify groups, we have to find the parent. How do we do that? We find the longest chain or continuous chain of carbons within a hydrocarbon. So we saw already 1, 2, 3, 4, 5. We could have a pentane parent chain. Pentane is our parent, and ol, our ending, is YL. We have an ethyl group. We're going to learn more in the next slide about this ol ending, but this is for the group, particular for groups. Now again, we have to find the longest continuous chain of carbons to find the parent. So where is the parent below? We'll get to the full name later, but we can consider 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Now I'm going to go on this line of carbons, not because it's on the horizontal, so don't be fooled. Sometimes those parents aren't along the horizontal. But I'm going to circle this one because we're going to use this rule. If 2 of equal length, then we're going to go with the greater number of branches. The number of carbon-carbon bonds you cut gives it away. 1, 2, 3. If I circle this, I only cut twice. So here, circling on the horizontal, 3 times. Whoosh, whoosh, whoosh. If I go along this line, whoosh, whoosh, only twice. So we go with a greater number of branches. Let's look at how we name groups. Now we kind of have an idea of how to get parent. Let's figure out what the names for groups are, and we'll put this all together and we'll be done. Groups, alkyl groups. I'm talking about the point of attachment of the group to the parent. So think of this purple as the parent. Starting where the parent is, we can have everything off of the purple is group. So, sorry, let's take that a little bit further away. The point of attachment of the group to the parent. So this is our parent, and let's count this as part of the group. This purple point is the first carbon, let's say, in the group. So 1, 2, that would be ethyl, since there are 2 carbons. Again, we're counting this purple point as being the part of the group still, but it's going to be attached to the parent. The parent here, maybe some long chain. 1, 2, 3, that would be a propyl group. And you can see the idea as far as ethyl to propyl, we've gone from 2 carbons in this group to 3 within this group. Ethyl from ethane and propyl from propane. Now if we connected not at the end of this propyl chain but at the middle, so it's connected to the parent from this middle carbon, we would say that's the isopropyl group. It's still propyl, but we're connecting through a carbon between 2 methyl groups. That's a methene, a CH group. So we call it an isopropyl group. Remember, that's a kind of a common name that's accepted for the group that we may be using later. Another common name that's used is sec-butyl, taking a butyl group and connecting it not just from the end, but from the methylene carbons, the secondary carbons within the group. Tert-butyl, connecting it from the tertiary carbon within the group to the parent. We call that a tert-butyl. And these are in italics, meaning they're not going to be considered when we order groups by alphabetic order. We don't consider sec and tert in italics. We consider if they're not in italics. Last, we can have for pentane, pentyl, if it's connected from the end, isopentyl, where we have the iso pattern on one end and we just count the number of carbons within the group. 1, 2, 3, 4, 5. So pent. But because this is connected to the parent, this is part of the group. We say pentyl, 1, 2, 3, 4, 5, isopentyl. We could do the same thing for connecting to the parent. Again, kind of getting the idea that we're connecting this pentyl 1, 2, 3, 4, 5 group. This is taking on the neopentane shape, but we call it a pentyl, neopentyl, because it's attached to a parent. When the parent is used, these become ols. Pentyl instead of pentane. Neopentyl instead of neopentane. Just as an example of how iso patterns can be used in other naming, we could have an isohexyl amine. This is the amine, it's the parent, and we have off of it 1, 2, 3, 4, 5, 6 carbons. We see the iso pattern at the end, isohexyl. Now 2 more slides as far as naming, and then we'll, I guess, finish with just a slight discussion of ring structures. So let's review a little bit of what we've learned. We know how to find parent. Longest continuous chain of carbons. If 2 of equal length, go with the larger number of branches. So we went with this one. And we have right now 1, 2, 3, 4, 5, 6 hexane as our parent. And we need to find offspring, substituents, children, groups. So we have 3, this group, it's an ethyl, because the group is attached from this carbon to the parent, and that's 1, 2 there's 2 carbons, that's ethyl. This would also be ethyl. And of course this would be methyl, having only 1 carbon. But we just can't say diethyl, methyl, hexane. We need to know where these are connected to the parent chain. So we have to number the atoms in the parent chain so that we can number the groups. Well, we number beginning nearest the first branch point. So here, 1, 2, instead of 1, 2, 3. So this would be carbon 1, 2, 3, 4, 5, and 6. So we've numbered our parent chain. If we have equal distance, for example, if the 2 first branches were equal distance, then we go to the second closest branch. Smallest number at first point of difference wins. So we may have to go to the second branch coming in from one end and compare that to the second branch coming in from the other end. Whichever wins in the second round. That has, I guess, the effect of making that end number 1. Now we know not only the names, but we know the numbers. So we'd say, oh, this is 1, 2 methyl. It's connected at the 2 position of the parent. This would be 3 ethyl. And this would be 4-ethyl. So we can put together the group names. We have the parent name in one full name. Write the name as a single word. If multiple identical groups, use di, tri, tetra. Well, we have that. We have 4-ethyl, 3-ethyl. So we can use di-ethyl, 4,3-diethyl. Now the di is not considered in alphabetic order. So I'm going to underline the E and underline the M. E comes before M. So we're going to go ahead and say E coming before M. We have 3, 4, di-ethyl. 3, 4. Di, meaning we have multiple groups. Ethyl. 2, methyl. And then this is there's no dash. There's actually no break either. Just doing it to give a pronounce the parent from the groups. But there's no break in between. So again, for di, we don't count the D and the I. It's in italics actually, and we have the E counted alphabetically, and that's before M. So it goes first. For sec-butyl and tert-butyl, we would also skip the sec and the tert and just consider the B's. But for iso and neo, you actually consider the I in iso and the neo in neopentyl, for example. Let's do this one more time, and we'll be almost finished. If complex substituents exist, what's a complex substituent, you might ask? Well, it's when we have a branching within a branch. So we can look at this molecule here, try to find the longest continuous chain of carbons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Doesn't look like anything's going to compete with this. Our longest chain, 1, 2, 3, 4, 5, 6, 7, 8, is octane. So we have our octane. Oops, that's fun. Let's put that up here. I need this for my groups. Octane is our parent. But we notice within this branch, we have a branch within a branch. So we can't just, without lifting our pen, trace that group. We have to pick up our pen to get this other methyl group. That's a complex substituent. We name it as though it were a separate compound, wherein the carbon attached to the parent is carbon 1, and we end the name with YL instead of ane. So for example, in this case, we'd say this is 1,2 or 1,2 ethyl, but off of it we have one, this should be a little bit larger, sorry, methyl. So we have this whole thing in brackets. 1 methyl ethyl. Let's put that down here. 1 methyl ethyl. Now I'm going to put brackets around the whole thing because it's going to be connected to some position. This is the naming of our complex branch. We have to take the carbon at the first point of connection and find our longest chain. That's the ethyl, and we still are ending it, so this is like a sub-parent, ethyl. And off of that, ethyl is at the 1 position of methyl. This is always carbon 1. And this is carbon 1 to 2. So it's ethyl, but it's off of this we have a methyl group. So 1 methyl ethyl wraps up this complex branch. We still need to number that group. So let's do that. Where's our first carbon 1 in this longest chain? 1, 2, 3. 1, 2, 3, 4. Oh, it would be this one. 1, 2, 3, 4, 5, 6, 7, 8 is how we number our parent. So this would be off of 4. So it's the whole thing in brackets. Even though it's a complex group, it's still off of the true parent. This is our sub-parent, ethyl. Let me just put it in dash here. This is kind of like our sub-parent. And then off of that was the methyl group, but it's all off of carbon 4 and the true parent, or the full parent, however you want to say it, the sub-parent, full parent. And we have other groups. We have our 3-bromo, we have an ethyl, we have our 5-ethyl, I apologize, I'm looking at my notes here. This can also be called by a common name, this 4,1-methyl ethyl, can also be called 4-isopropyl. We can wrap up the full name of this group, because it's an isopattern group, as 4 off the 4 carbon, isopropyl, 1, 2, 3 carbons in that isopattern, and it's a methene, a CH group with 2 methyl groups off of it, so it's isopropyl. We can capture this group calling it just an isopropyl group. Now let's write this as a single word. Now I'm going to go ahead and consider alphabetic ordering. I have a B in bromo, I have the M in methyl ethyl, and E in 5-ethyl. So we can name it 3-bromo dash, we're going next 5-ethyl dash 4 in parentheses, or I'm sorry, brackets, 1-methyl ethyl octane. Now the other name we could have used is using the 4-isopropyl, 3-bromo, 5-ethyl, 4-isopropyl octane, and both of those are acceptable. And that's our second example, and we're sort of just finishing there with a full problem, or going to a structure and finding the full name. Just want to mention what we do if we have ring structures. For ring structures or cyclic structures, find the parent chain, and usually it's the ring, but if the group off the ring has a chain of carbons that are greater than the number in the ring, then the group off of that ring becomes the parent. So example of this is cyclohexane here, 1, 2, 3, 4, 5, 6. The group off of the cyclohexane has more carbons, 1, 2, 3, 4, 5, 6, 7, 8. So this becomes the parent, octane, and the cyclohexyl group is off of the second carbon in. So we have 2-cyclohexyl octane. Now if we don't have that, and we have the parent as being the ring, number the carbons in the parent species in the same way we did with non-cyclic species, where we have the first branch or point of difference being closest. So with smallest number at the first point of difference. So if we think this is carbon 1, then we have 2, 4. But we can also consider this one is 1 and would be 2, 4. So this one, we don't have a way to say the smallest number at first point of difference, except to say, well, I know this one can't be carbon 1 because the smallest number is 2, 2. But if I use this as number 1, put an asterisk by it, we could have our first point of difference be at this carbon. We have a 2 position that has a group off of it. And then 4, 1, 2, 3, 4. But we could also consider this position, because it's same smallest number at first point of difference, 1, 2, 3, 4. Now the only way then we can really name this is by going to the alphabetic consideration. So starting with an ethyl first, because it comes before methyl. So we can say, no, this will be the winner, not because it has the smallest number at first point of difference than this one, but because it has an ethyl group off of it. So 1-ethyl, 2,4-dimethylcyclopentane. Not 1-methyl and then going around the other way, ethyl and methyl. So we chose this one because it has alphabetically a greater, I guess, or lower letter in that alphabetic ordering. Comes at the first. Now we know it's certainly not this name here, where we have our carbon, I guess 1 here, 2, 3, 4, 5, because that's going to give us a much larger numbering here, 1, 2, 3, 4, 5, 1, 3, and 5. Usually you can just generally know you're on the right name if these numbers add up to a smaller number than what you're proposing or looking at as an alternative. The lowest total, 1 plus 2 plus 4 is 7, 5 plus 1 plus 3 is 9. So this is not the name. we want to have the smallest numbers at the first point of difference. Well, that's it. We'll be looking at conformations in the next video, where we're looking at not just molecules in their name, like for this one here, 4 carbons in a chain, and a bromine off of the carbon 2. We'll be looking at conformations of the molecule. This one would be 2-bromobutane. So the next video looks at looking at conformations of the atoms around the bonds that we can rotate around. These are looking at conformational analysis. Bye-bye.